L3 VPN, right? So as I said, if you have any query, feel free to let me know. I'll try to explain all those things when I'm explaining the main topics, right? So before going into the topics, my name is Fakrul Alam. I am the Senior Training Officer here in APNIC. You might know what is APNIC. So we are the regional internet registry in this Asia Pacific region. So our main core business is to provide IP address and AS number in short to the members to this region. Along with that, we do a lot of training activities, training and development and collaboration. So my responsibility is to do training uh, in different topics. My specialties goes on routing and switching. I do a lot of security, IPv6, DNS, DNSSEC, and also MPLS, right? As I said, at the end of this presentation, I'll share a link with you to do a small survey, and do let us know how we are doing in terms of this e-learning. So we do this e-learning every Wednesday on 3 topics. This is the last one for today. So for details, you go to training.apnic.net, and we have all those scheduled for next couple of months, right? Great. So the agenda for today is MPLS VPN. So I'll explain what is MPLS VPN and what are the services we could provide with the VPN. There are few terminology related to MPLS. There are VRF, RD, and RT. I'll explain what is VRF, RD, and RT, and why all those things are critical for MPLS designing, especially. Uh, then I'll show you how the control plane and data plane in MPLS for L3 VPN works, right? And few configuration snapshot. So how you configure a Cisco router for L3 VPN, right? So I think you have a prior idea what is MPLS, what is control plane and data plane, right? So I'll go and explain those a little bit for you if you want. So before going to MPLS VPN, I think you might know what is MPLS, right? So we called it a multi-protocol level switching or swapping. So the whole idea is in IP backbone, in IP core, we do IP, right? It might be IPv4 and IPv6 in layer 3. So it is very, very critical to run parallel infrastructure. In what I'm trying to say is that you might have some other legacy infrastructure like SDH, ATM, frame relay, and so on. So, and we usually provide services on top of it. So we provide VPN service on top of IP backbone. We provide VPN service on top of ATM network. So what MPLS does is, and I think you might know IP works in layer 3, so IPv4 and IPv6. So what MPLS does is it does all those switching based on level, not based on IP header. So it put an additional header in between layer 2 and layer 3. We sometimes call it shim header. And router, MPLS capable router will do the forwarding based on these levels, not based on IP. So what are the benefit we are getting out of it? So regardless whether it's an ATM, IPv4, IPv6, or some other technologies, if you have MPLS, you can seamlessly send your data across your MPLS domain, regardless what you are running on the top level, right? So that's one of the beauty of MPLS. So that's why we see a lot of carrier or telcos are moving forward and having MPLS in their core or backbone. One of the advantages or the services we provide, which is very, very popular, is MPLS VPN. I think you might know what VPN, like virtual private network. And we could have MPLS to leverage the VPN services. So if I give you a traditional example of VPN, how you do it in IP world. So we call it overlay VPN. So if you are an ISP, I'm your customer, I go to you and say, okay, I have 10 sites. Could you please connect all these 10 sites with my head office? So maybe full mesh, right? So as an operator, what you could do is you do overlay VPN. So you create tunnel across all those 10 sites and allow me to send traffic across your infrastructure, right? Uh, that's one way to do it. Other way is what the enterprise are doing is I get an IP backbone from you, then I do tunneling with IPsec or something else or GRE, whatever you do, and I have my VPN tunnel ready. So that's the traditional way of doing VPN in IP world. We can leverage this service of having VPN in MPLS, and we'll describe all those things in later, right? So the VPN in MPLS could have in two flavors. We could have layer 2 VPN and layer 3 VPN. As the name says, layer 2 is for a layer 2 broadcast domain. We could have VPWS for point-to-point layer 2 VPN. We sometimes call it cross connect. So if you have point A and point B, I connect to both of your site using L2 VPN. That means you have a layer 2 domain in these two offices. There might be some other other routers in between these two sites, right? So yeah, welcome to the eLearning. Yeah, so that's one we have in VPWS. So we call it point-to-point layer 2 VPNs. We could have VPLS, which we use for the point to multi-point layer 2 VPN. So it's the same thing, but now in terms of in two location, now you have 4 or 5 or multiple locations, more than 2. So you have a layer 2 broadcast domain among all of your offices over a MPLS domain. So that's what we have in L2 VPN. The whole idea is having a layer 2 infrastructure on top of an ISP. Then we have layer 3 VPN. We call it, and we could have it using BGP or MPLS IP VPN sometimes. So it depends on how you do the signaling. So we could use BGP for the MPL for the signaling, or we can use MPLS LDP or some other protocol for the signaling. But in general, we have two types of VPN services based on the topology of the services you want. It could be layer 2 or layer 3, right? So the advantages we are getting from the MPLS layer 3 VPNs are scalability. So what I mean by scalability is, if I give you the same example for overlay VPN. So what ISPs are doing is, if my customer has 10 sites and he wants me to do a full mesh layer 3 VPN, so what I have to do is I need to connect all those 10 sites in full mesh. So maybe n into n minus 1 divided by 2, right? So how many mesh you have? And the problem is, if it grows, if I have 100 customer, everyone having like 100 sites, is not scalable, because I need to deploy all those overlay VPN infrastructure on behalf of my customer. Number one. Number two is, if a new sites add to the VPN domain or VPN domain, what I have to do if I'm doing overlay VPN, I need to go to all those 100 routers and make a tunnel with the new one. So in terms of operational and management, is not a good job or a good way to doing all those VPN overlay VPN. It adds a lot of complexity in your O&M. And number three, there is a way of doing it, because you could do some scripting and other, but it doesn't scale in a long run. So that's what we mean by scalability. But if in overlay VPN, but if you do MPLS VPN, we leverage the MPLS level swapping, and we can have VRF for each customer who has their own kind of namespace in the router, and we use BGP signaling, for example, to signal all those routers in my core edge. We call them P router, provided edge router, to send the MPLS signaling and create a VPN tunnel. So to add a new customer, if I'm an ISP, what I need to do is I need to enable the VPN services on that specific P router and add your router or your offices in that particular VRF, right? So in terms of deployment and scalability is very, very easy and scalable. L3 VPN is somehow is secure also. So everyone has their own namespace. We call that VRF. So one VRF, for example, VRF A can't interact with VRF B until unless we tell them to do so. So if all of them are isolated from the provider edge perspective, and allow, if you see, if I have anything in my core, like the P router, so those are not VRF. They don't know anything about the VPN and layer 3 VPN or layer 2 VPN. What they do only the level swapping. So for their case, it's very, very easy. It's easy to create, as I said. If you want to deploy new services, you just enable the MPLS, that particular address family on that particular P router, add an associated interface to the VRF, and that's it. You're done. And based on RT and RD, your MPLS router will export and import all those information. Flexible addressing. If you have experience handling VPN circuit in your infrastructure, if you're from ISP, what you see, most of the cases, all those enterprises use RFC 1918 private address block, like 192.168.0.0, 10.0, 172.16. So if I'm a customer A, I use 192.168.10.0/24. If you are a customer B, can you use 192.168.10.0/24 in the same infrastructure? No, you can't, because there's a conflict of address. How the ISP router will route all those things with the same address block? So it's an issue with layer 3 VPN. So sometimes ISP does netting. So they do net all those private address to a public address and vice versa, which is not a comfortable task to do. But in MPLS addressing, the advantages we have is we have isolated namespace as VRF, right? Every customer has their own VRF. And customer has the flexibility to choose their own address scheme. So if you're customer A, you're using 192.168.0.0/16, for example. I'm customer B, I could use 192.168.0.0/16 in the same MPLS domain, because MPLS will distinguish those private addresses or addresses via route distinguisher. We'll explain all those things later, and make them unique in your MPLS domain. So from my 192.168 IP address will not conflict with your 192.168 IP address. In the MPLS domain, they will be treated separately. Integrated quality of service support. So with the leveling and swap leveling, we can tag with the QS. We can do traffic engineering, which is much more scalable than your regular IGP traffic engineering. And the last but not least is straightforward migration. So what it says that you might have MPLS you might have an ATM backbone, you might have frame relay IPv4, IPv6, IP backbone, and you might have hetero infrastructure, and merging all those things in MPLS domain is very, very easy. So you run MPLS, you have all those overlay infrastructure, and you can send everything across the MPLS domain. So that's why it says the migration is pretty much straightforward in L3 VPN. So if you remember the MPLS or MPLS topology, so there are three critical components. One is C, we call it customer edge routers, what we have right here. If I try to draw, so we have C router, customer edge router. All those routers of CPE are in customer premises, so they belongs to CE. Then we have PE, provider edge router. So PE belongs to the ISP, but they connect CE. So any router which is connected to CE in general, they are PE. We call it provider edge router. And in the core, in the middle, we call them pre-router or provider router. What they does is they are the core router. They do MPLS level swapping. They will not do any push on pop or MPLS swapping. Level swapping, they do the level swapping, but not push and pop, nothing. So for them, it's very, very transparent. They see in 11 in level and associated out level, and they do the swapping. That's it. But for P, they have some additional task. They connected with C with some other routing protocol. They need to, for L3 VPN MPLS, they need to import and export some values. We explain all those things. We call it RT, route target, and send them across BGP, multi-protocol BGP, right? So if you see a traditional L3 VPN diagram here, so we have a VPN A customer here connected to another VPN A customer. So they are in the same VPN domain, but for the ISPs in the middle, they will do the MPLS level swapping for them. That's straight. They don't know, for the P router, they don't know about all those VRF or VPN, right? So as I said, there's a concept called VRF, virtual routing and forwarding instance. What it does is, if you have experience in virtualization in server world, so we do virtualize our server, right? We do VMware, VirtualBox or something. So what it does is, you're running an OS, but on top of it, we could run some other OSs. So you're running Windows, on top of it, you just divide it with it with another Windows version, with Linux, whatever you want. So all those virtual boxes or containers are isolated with each other, right? So they have their own kernel, own networking interfaces, and we virtualize our interface like this way. So in routing, VRF is kind of a same concept. We slice those routers in VRF in individual virtual routing and forwarding instance for each and individual customer. So we do, so if it is for VPN A, for a specific customer, in my P router I create a VRFA, for example. You name it how you want. For a VPN B, I create a VRF called VPN B, and we create all those things in our P. We don't have to touch our P router or provider router. Only we do VPN configuration in our P router. And this VRF definition defines the VPN membership of a customer site attached to the P, and VRF associated one or more customer interfaces. So if I have a new customer, what I do, I create a VRF in this P router and add an associated interface with this VRF. That means this C router is under this VRF via this interface. So that's the whole idea. But in general, VRF is the same. We have virtualization in servers, creates an individual container, if I name it, for each and individual VPN client, right? So when we have the VRF ready, how you send all those signals? Because if I go back and show you this diagram, so sorry, if I have VRF here, if I create individual VRF, and how this P router will send this information across the MPLS domain to other P router, right? So that's the next challenge we have, because we understand for each VPN customer you are isolated with a VRF, but how those VRF will be sent, or all those data will be sent across your MPLS domain. For that case, we use MP protocol, MP-iBGP. We call it multi-protocol BGP. It's the same BGP we do for internet, BGP version v4, but we call it MP-iBGP because it supports multiple protocols. That means it could support IPv4, it could support IPv6, VPLS, VPWS, all those things. That's why it is multi-protocol. So what P router use the MP-iBGP to distribute the VPN router to each other, and this MP-iBGP customize the VPN customer routing. So if I have a P, if I try to draw here, this is a P router, and I have a customer connected, two customer connected, right? So this one is using 192. Sorry, my bad. My drawing is not that clear, but to get you an idea, so they are using the same address block. So how this P router will distinguish these two IP addresses. They're from the same address block. So they use a technique called RD, route distinguisher, to distinguish this route uh, from the customer. And we also have a concept called RT, route target, and VPN level in L3 VPN. So these are the three techniques used by the P router to establish a L3 VPN or deploy an L3 VPN service. So what does an RD mean? RD is route distinguisher. As the name says, it distinguishes the router across the customer, right? Is 8-octet additional information. So if my IP address is 10.1.1.1, I could use type 1. It's kind of a community value, looks like that. So you could have a 100.1 the way you put it, or you could have an IP address, your router address :1, type 1. So what the idea is, in a P router, when I have your IP address 10.1.1.1, the way I configure the RD, append the RD with your IP address. Now you have a unique RD and IP address. If I add it, these two will create a unique VPN v4 address. We call it VPN v4 address, right? Now, and this is unique for each customer, and that's how we segregate the IP addresses from the MPLS domain. So if you see this diagram, this customer is using 10.1.1.0/24 VPN-A here on the top, and VPN-B is another customer using the same IP address. In the P, what I did is I use 100:1 as the RD for VPN-A. So this one is for A, and I use 200 for 1 for the customer VPN-B. So now, if you look at these two individually, 100:1:10.1.1.0 and 200:1:10.1.1.0, these are two unique VPN v4 address for this P or for this MPLS domain, right? Though it not look like an IP address, but for the sake of argument, like these are the IP address. Now for this router here in P, for him, these are the two unique VPN v4 address. So they will not conflict with each other, right? And as I said, P router use MP-iBGP to advertise this VPN v4 route to the MPLS domain. Right. So that's what we have in RD. So the first challenge, if I recap, how I distinguish all customer, I use VRF, right? I have separate VRF with a separate interfaces. I overcome the challenge of having the same VRF, connecting multiple customer. The next challenge is how I distinguish all those addresses, because customer A might have the same address with the customer B, right? In the overlay, we need to design our address like that there will not be any conflict of address, or there might be a chance that customer will come up with the same address. So that was an issue. So how we recover, how we solve this problem? We introduce RD, route distinguisher, right? Or T, the D. So what it does, that we append a unique 8-byte information with each customer address and make it a unique VPN v4 address, right? So the next is how we send those information. We'll send those information using MP-iBGP multi-protocol BGP. Now the next challenge is when this P router, if I try to do a diagram, sorry, my diagram is not that good, but to get an idea. So I have a P router, right? Two P router, and I have one customer connected here and another customer connected here, and in between I have MPLS domain in between. So now I have VRF here. I use RD to distinguish. I send it using MP-iBGP, right? Now the problem is this P here. How does it know? Because I might have another P here, and in this P I might have multiple customer. So how this P knows whether this route or this VPN information is for him or not? How does it know? So we use RT, route target, to solve this problem. So is also a 8-byte community BGP community attributes. It looks like same with the RD. You can use the same value for RD and RT. So what we do is we add these and we export and import RD. So when I receive any prefix for the customer or send it across the VPN or the BGP, sorry, MP-BGP, I export an RT. Okay, for this prefix X, I said RD is 100:1 and send it via MP-BGP. And this P router here, it has a command called import 100:1, right? So when this P router here via MP-BGP receive this information, he said, hey, I have import information for 100:1. I have something for this prefix as X, and then this prefix will import those information to his router. That's what we use RT. So to RD we use to distinguish the prefixes route, and RT is to define which prefix goes to which P router, right? So any question or confusion regarding VRF, RT and RD? Any query? No? Okay, I'll move forward and see what we have next. Okay, so this is the example of RT. So if you see this, we have a P router, P1 and P2. We have the MPLS domain. We use MP-BGP to send the information. Now I have two VPN, VPN A, VPN B. They have two sites for the sake of argument in here in this example. So what this P says, so if you look at this, what it is, 200:1:10.1.1. So is a VPN v4 address, right? And it has an RT 200:1 and 300:1. So if I look at this P1, it says for VRF1 import 100:1 and export 100:1. If I see in the P2, it says import 101, export 101. There might be some other for other VPN, other sites. But looking at this RT, import and export, I understand what I could understand here is all those VPN v4 associated with these import 100:1 going to this P2, they'll export it, they'll import this 100.1 for this VPN A VRF. The same with 200:1 and 300:1. So if you see VRFB here, this 10.1.1.0/24, it exports as an RT 200:1. It comes across P2 and P2 VRFB. This interface says import RT 200:1. That means this prefix VPN v4 will be imported to this VPN, right? That's what we do with the RT. Right, so now we have RT, we did RD, and see, okay, and we use RT to configure the VPN topologies, sorry. So whether it's a full mesh or hub spoke. So, and this import and export skill set is very, very important. If you understand how you do import and export, creating VPN topology is very, very easy. It's kind of a piece of cake for you. So if you look at the diagram on the left here, so if it is a full mesh, what we are doing is we are importing the same RT and RD. So this side here, if I name it as A, it export everything with 100:10 and import everything 100:10, and is the same across all the sites. So that means all those sites exchange the same prefix. I mean, exchange all the prefixes among themselves. That's what we have full mesh. So for example, if I have a new site here for the same customer, for example site X, it has the same export. If it does import, for example, if it does import 100:10 and export 100:10, your VPN site is up. You don't have to do anything and go in individually all those sites and change the import and export. It's that easy, right? So that's why we said service deployment is very easy in MPLS L3 VPN. So that's what we have in L3, right? Sorry, in full mesh L3 VPN topology. We could have a hub and spoke, as the name says. So we have a hub, for example, maybe your head office somewhere in location X, and I have three sides, 1, 2, and 3. So what if you look at the RT is very interesting. So what we're doing is that we are importing 100.12, which we export in our head office. If you see, so we export 112 and we import in other side. We export 111 in all the sites, and we are importing here in head office. That means this site 1 can only communicate with site 2. I mean hub site. This 2 is only hub site. So all the traffic basically going via the hub, not via the spoke. So spoke they can't communicate. If they want to, they need to go via hub. So this scenario sometimes is very ideal for maybe for the bank and enterprise when they have their centralized VPN, centralized firewall and other security appliances. They want all their traffic to be routed via their head office or data center. They don't want any branch to branch or site to site communication, right? So this RT is very strong concept, I will say. So if you understand how this RT import and RT export works, you can design any kind of any topology for L3 VPN, right? So when you have these things done, now we have the VPN level. So when everything is done, P adds the level for the NLRI field. We call this next level reachability information. That's one of the biggest concept in BGP. So we have RD, then we have RT, and it adds a associated VPN level for that prefixes and send it via MP-iBGP. So the one associated in P1 as a local level, for P2 it will be the outer level. So when the data plane starts working, it tags these prefixes with VPN with outer level 100, so that this P router can do the level hop or swapping. Right. So let's see how the control plane works in MPLS. So in step 1 here, P receive an IPv4 update from the CE1. So it might be eBGP, OSPF, ISIS, static, you name it, any routing protocol. When routers P1 receive is P1 converted into a VPN v4 address, right? If you remember. So it will add a 8-byte RD and convert it as a unique VPN v4 address and send an MP-iBGP update message, construct an MP-iBGP update message. And while doing it, it associates RT, route target. In our case, it has 200:1 per VRF. It changed the next hop to P1. So for other routers, for this P router to reach these prefixes, next hop will be router P1. And assign an associated VPN level 100 local level and install in the MPLS forwarding domain. So that's what's done by Lalit in phase 2. In 3, P1 sends an MP-iBGP update for the other P routers. For P router is transparent because they have a IBGP session with this P router. So P2 will receive all those updates. When P2 receives this update, P2 will check whether the RT is locally configured as an import route. So for him, what is exported by P1 need to be imported by P2 within any VRF. If it is matched with this RT 200:1, P will translate this VPN v4 address to an IPv4 address. So it removes the RD and update the VRF safe table for these prefixes 10.1.1./24 with a level of 100, which was given by this P1, right? and in step 5, P2 advertise this IPv4 prefix to the CE2 using whatever routing protocol you have, right? So we receive some prefixes here, we convert it to a VPN v4, add an RT, add an associated level for it in level, and send it via MP-iBGP to the other P router. P router check this and see whether they have their associated import RT for that. If does match for any VRF, strip off the RD and create a unique and convert it to a IPv4 prefix and send it to the C. And before doing that, it will update the VRF safe table with an associated level assigned by P1. Right, that's the whole control plane we have. So, and we use LDP for the MPLS backbone to swap or exchanging all those LDP level information or local mapping with each node, right? So when we have this control plane done, signaling done, now it's time to exchange data, right? Let's see how the data plane works. So P2, so now this C2 will communicate with this prefix 10.1.1.1, for example, IP packet in site 2. So C2 imports 2 level for each IP packet going to the site 2, because the first one is a tunnel via LDP, which we sometimes call as a transport level, the outer level, and add the VPN level. For our case, the VPN level is 100, and we have the outer level which is assigned by this P2 and swap across these P routers. And P1, I think it should be P1. The P1 P1 here will does the penultimate hop popping. So it swaps the, so if I go one by one, so it adds add 2 level. The inner level is 100 is a VPN level, and it adds the associated transport level 25. It comes to P2. P2 say, okay, if it is in level 25, outer level will be 50. Swap the level and send it to the P1. P1 check is outer level is 50, and for it as a PHP router, the router before the last hop, it does a penultimate hop popping. That means remove the outer level, it removes the 150 and sends this to P1. So for P1, it has only the VPN level and the prefixes. And P1 retrieve that because it knows it assigned this 100 as a local level, and it knows if it is 100, then it will goes to C1 via this VRF. So what P1 does, it removes this out the level, the VPN level, create a IPv4 packet and send it to C1. Right. So how do we configure L3 VPN? On Cisco router, we need to following C communicate with each other. So if you look at here, we need to have a running IP backbone. So that means IP address are configured. P and P routers can communicate. We have MPLS network fully configured, right? And we have IGP for the next hop reachability, right? When you have all those things done, we enable MPLS in the interface. So it's a 2 command. So we need safe Cisco Express forwarding for the MPLS, but per interface we say MPLS IP and we enable LDP. That's it. When it's done in the P router, we create a VRF. We call it VRF definition. You name it whatever you want by customer name. We create an RD route distinguisher. For this customer, my RD is 100:10, and I have the same import and export. So that means anything export with 100 and 100 will be imported by me. Address family, and we add the interface. In that case, first Ethernet 0/0. This one. If you look at this diagram in this previous way in here. So I associated this interface with a VRF. So I create a VRF, I assign this VRF to this interface, first interface 0/0, and IP address will be under this VRF, not under the physical interfaces. Then we activate the MP-iBGP. So this is the regular BGP command router BGP 100. We go to address family VPN v4. You see, this is a new address family VPN v4. We create a neighborship with the iBGP neighborship with the remote P, and we say send community because RT is a community value. Right. Then if we do eBGP between PE and CE, we create a BGP configuration under the specific VRF. So if you look at router BGP 100, this neighbor configuration is not under the address family. IPv4 is under the address family IPv4 VRF VPN A. So it's a VRF specific configuration. We activated this neighborship. That means C and P is doing eBGP. And now we run all the configuration in VRF specific domain. So we say show BGP VPN v4 unicast VRF name. For IPv4 global unicast, what we used to do, show BGP IPv4 unicast summary or unicast, that will show all the route. If it is a VRF specific, we'll run show BGP VPN v4 unicast VRF name, and we see all those routes specific to the VRF. Right, and you see the interesting thing where is this route distinguisher 100:10, the one we associated with this specific VRF, right? So we have the CP done, and if we see from the C show IP route, we'll receive these prefixes, because for the C is transparent to them. They don't know whether there's any MPLS running or not in the provider core. They'll receive this as an eBGP prefix, and the next hop will be the P router. Right. So configuration wise is pretty straightforward, though you have a couple of syntax. To recap, the configuration is you create a VRF, you associated customer interfaces with the VRF, then run some kind of protocol with the VRF. If it is eBGP, you don't have to do any redistribution. So it's pretty easy. So I receive eBGP prefix from my C router from a customer. I send it across MP-iBGP to the other P router. Based on the RT and RT import and export, the P router will import it to the associated VRF, and with the routing protocol running on, in that case, for example, eBGP with the other part of the C, it will send all those prefixes to the C router, right? So if I see the C router routing table, for them is kind of a eBGP prefixes for them, right? So there's a quick recap on L3 VPN. So it's already close to the time. So if you have any query specific to L3 VPN regarding VRF, RD, RT, control plane or data plane of the L3 VPN, feel free to let me know. I'll try to answer all those questions now. Or if you don't have any query, I have my email address in the slide, I think in the first or second slide. I have a question from Himira. Can P share an interface for several VRF nodes? So one interface for one customer, one VRF. So what ISP does, they put some switches, they do VLAN, right? They do router on a stick. So if I have a router connected with, so for example, if I draw something, so I have a router, I have one interface only, for example. So it means I can only add this interface in VRF. If I have 100 customer, I need 100 interfaces in my router, not feasible. So what I do, I put a switch, for example, 24-port switch. I do VLAN, right? And I put all those sub interfaces in individual VRF. That's the ideal way to do it. But yeah, to answer your question, one interface one VRF. Right. So if you don't have any query, what I'll do next is so this is the link for the survey. If you have time to go to this link and do a quick survey for us, the next I'll share the slides with you. So if you go to this link, there's a survey link, and this link is the FTP server to download the handout for this presentation. Right. So if you don't have any query or comments, we can finish our presentation for today. Thank you everyone for attending this e-learning. Hope to see you soon in some other e-learning. Thank you very much.